hydrodynamics, we'll be discussing where the fluids will be moving. Till now, we didn't discuss the motion of the fluid. Fluids were at rest for us. Now the motion of the fluids will begin, and that is known as hydrodynamics. So first topic is viscosity. What is meant by viscosity? See, these are the layers of the fluid when the fluid is in motion. So viscous force is like the frictional force which is acting within the water. Suppose this layer, if I'm talking about all these layers, if they are moving, let's say with v velocity on the right side, so each layer will be rubbing on each other. See, this layer, let's say it's moving on this is moving forward. So a viscous force will be acting in the backward direction, which will be providing resistance to flow of motion. Understood? This is like you have already heard of frictional force. In friction, what happens when two irregularities they are getting rubbed over one another? So one force is there, and on the opposite side you get the frictional force. So viscous force is exactly the frictional force in your fluids, the same frictional force in your fluids. So this will be providing a little resistance. So suppose if I tell you water, if you take some drops of water on your hand and if you rub it, you will find it very smooth and it is just slippery. But when if I tell you take some honey and then rub it, you will find a little resistance in moving it. That resistance is because of the viscous force, and this is dependent upon the material. That's why we are having different materials and different viscous force. So what is meant by viscous force? Viscous force or viscous drag, both are the same term. Backward dragging force is developed, which opposes the motion of the liquid. It acts tangentially on the layers. When a liquid or a fluid flows, a backward dragging force or viscous is developed between its layers that retards the motion of the liquid. The viscous drag acts tangentially on the layers of the liquid. Write it down and I'll tell about coefficient of viscosity. Now coming to the coefficient of viscosity. So see, if this is one layer of liquid, this is another layer of liquid. This is moving with velocity v, this is also moving with velocity v. It's just that the relative velocity, that is the change in velocity which is occurring, that is dv. So this is added on it. Because if viscous force is acting, it means one layer is ahead of other. That's why the viscous force is acting between them. So this is the additional velocity. This is the right side, this is the left side. So towards the right side they are moving. On the left side, viscous force is acting, and A is the area of the slip. Between the liquid layers, the separation is dx. Dx, dv, these are very small terms. So this is also very small, this is also very small. Now see, I have told you, whenever you change something with respect to time, we call it as rate. Like in velocity, we say rate of change of displacement, because displacement by time. Or we say acceleration is rate of change of velocity, because it is velocity by time. But if the same thing is getting divided by position, that is x, we call it as gradient. So here velocity getting divided by position, this is known as the velocity gradient. So see, the viscous force depends upon two things. Firstly, the area of the surface. Second, this velocity gradient. So totally it depends upon a dv over dx. Now, as usual, when you will remove the constant, this will give you eta. This is a constant that is used here. A dv over dx. Understood? Eta is the coefficient that is coming. As a constant, this is coming. See what is meant by every term. F is the viscous force which is acting. A is the area of the layer. Area of the layers, both the areas will be the same. dv is the velocity, basically relative you can say, or the change with respect to one another. Similarly, dx is also the thickness, or you can say this is also the change in the thickness which is coming. This eta is the coefficient of viscosity, and this depends upon two things. It depends upon nature of material. That's why different materials have different viscosity and temperature. So the increase in velocity divided by the distance, that is dv over dx, which this change occurs, that is dv over dx, is called the velocity gradient and is measured perpendicular to the direction of velocity. So this is your coefficient of viscosity. Suppose this is a question. Coefficient of viscosity is 10 decapoise. Decapoise is the SI unit. This I'll be discussing. This is moving with 10 meter per second. Separation between them is 5 millimeters. And the each layer's area, the area of each layer is 2 meters square. So F is equal to eta A dv over dx. So coefficient is given as 10, area is 2, velocity is 10, and this is 5 into 10 to the power minus 3. So this will be 5 to 4 into 10 to the power 4 newtons. Like this, you will be using the formula. One more question we will see here. First, write it till here. Calculate horizontal force required to move a metal plate of area 2 into 10 to the power minus 2 meter square with a velocity of 4.5 into 10 to the power minus 2 meter per second. When it rests on a layer of oil, so this is the thickness, this is the coefficient of viscosity. See, area is 2 into 10 to the power minus 2. Velocity is 4.5 into 10 to the power minus 2 meter per second. This is meter square. Dx is 1.5 into 10 to the power minus 3. Coefficient of viscosity is 2 Newton second per meter square. So we have to find out the force, right? Horizontal force. So forces formula is eta A dV over dx. So this will be 2 into 2 into 10 to the power minus 2, 4.5 into 10 to the power minus 2, 1.5 into 10 to the power minus 3. So this becomes 12 into 10 to the power minus 1, that is 1.2 Newton. This should be the answer. Just match it. This is clear? Khadija, Mariam, Nuha.
Yes, ma'am.
Okay. Write it down, then we'll come to the units of coefficient of viscosity. Just the units are left, then we'll start with Stokes' law. See, definition of eta, coefficient of viscosity. This I told you. It's defined as tangential force required to maintain unit velocity gradient between two parallel layers, each of unit area. Viscosity of an ideal liquid is 0. Coefficient of viscosity of a liquid is inversely proportional to temperature. However, see, this is about the materials. This I've discussed. Let's come to coefficient of viscosity. This is the formula. Now see, force is Newton, distance is meter, area is meter square, velocity is meter per second. See, meter gets cancelled. Definition, this unit is Newton, seconds per meter square, which we call as decapoise. The CGS unit is just poise, that is dyne centimeter square, dyne seconds per centimeter square. Same thing when you'll convert it into CGS unit. So this is deca, so you just have to multiply it to 10 to convert. Deca means 10. Effect of temperature and okay. Write it down from here, then we'll see Stokes' law. See, Stokes' law is also an extension of viscous force. It's just that this is valid for spherical objects. Only for sphere you are going to use Stokes' law. Alright, so this is the viscous force that is acting on the spheres. Suppose this is the sphere, these are the layers of the fluid, this is moving with v velocity, backward viscous forces acting. So velocity of the body is v, viscous force is Fe, r is the radius of the body. Now the forces formula, you don't have any derivation. For the derivation of this question, of this particular Stokes law, you have to go by dimension analysis. So there was a technique to derive the formula by the powers, exponents powers of x, y, z. Then we used to equate the equation. From that only you'll get. So viscous force is 6 pi eta rv. Fe is again the viscous drag or the viscous force. 6 is a constant, pi is a constant, eta is coefficient of viscosity, r is the radius of the sphere. Because this is valid for sphere, so radius will always be there. And v is the velocity of sphere. All right. This, let me tell you this also. See, from this you can conclude, look at the formula. Viscous force is directly proportional to radius of the body and directly proportional to velocity of the body. So these are the two major components of the viscous force. So this is the viscous force on a spherical body. So viscous force is helpful, and it is used in Millikan's. There was oil drop experiment. This you will study in chapter 1 of class 12. There was an oil drop experiment conducted where viscous force was acting upwards, downwards, gravity was acting, electric force was also acting, and this was done. It accounts for the formation of clouds. It is used to find size of small particles. It explains why large raindrops hurt much more than small ones. So these are some applications of it. Just make the headings. This is not very important. This I would suggest you all to go through the NCERT and read the applications as a homework properly from the text. Write it down. Then we'll start with terminal velocity. See, now starting with terminal velocity, maximum constant velocity, definition we'll see later. First, I'll give an example. Suppose this is a bucket and I have filled it with a viscous medium. Viscous medium like honey, glycerine. If you notice, there's a difference between the densities of both the substances. If you take water in your hand, if you take oil in your hand, oil is a little viscous, more viscous than it. Then you take honey. When you rub honey, you feel maximum amount of resistance when you're rubbing it. Similarly, glycerine also. So any viscous material you can take and completely fill it. Now, if you throw a freely falling body, suppose here the velocity is 0 meter per second, it is at rest. As I've thrown, the velocity increases to 2 meter per second. Then the velocity increased to 2 meter, increased to 3 meter per second. Then I'm noticing the velocity is 3 meter per second. Again, it's falling, velocity is 3 meter per second. It's falling 3 meter per second. So this is the terminal velocity that has been achieved. This is the terminal velocity that has been achieved. All right. So what is this? Initially, there was this was going through free fall. Velocity was increasing, and then a constant saturation was reached. Why this occurred? Because the weight of the body balanced the viscous force and the buoyant force. When this state is reached, that these forces are balancing these downward forces, velocity becomes constant. Why? Because when the net force is zero, acceleration will also be zero. If acceleration is zero, velocity will be constant. That's why we get terminal velocity in our system. So maximum constant velocity acquired by a body while falling freely through a viscous medium is called terminal velocity of the body. Importance: viscosity of air or liquid is used in providing damping torque in measuring instruments. Oil used as lubricant should have proper value of viscosity. The viscosity applying brakes, blood circulation through arteries depends upon the viscosity of the blood. So this is how the graph will look like. Initially increasing, then a maximum saturation point is reached, which we are calling it as the terminal velocity. Why is the terminal velocity achieved? The reason that I gave you was, see, if the fluid is moving, if the block is moving, downwards is weight, viscous force is already acting, but when we're talking about fluids, we know buoyant force is also acting. So basically, the net force in your system will be weight will be balancing the buoyant force plus the viscous force. What is the weight? Weight is mass into acceleration due to gravity. How can you write mass? Density into volume into acceleration due to gravity. Density means density of the body. So this is your first equation. We'll just put all the values. What is W? What is FB? What is FV? So W we have achieved. Talking about FB. What is buoyant force? Sigma V sigma G. Sigma is density of the liquid. This was density of the body. This is density of the liquid. Second equation, FV also achieved. What is FV? We have just now seen 6 pi eta RV. That is the Stokes volume. This is the third equation. Now at equilibrium, all will be balancing each other. Right? At the equilibrium, this will be balancing. So basically, when we'll substitute it, all the three we have achieved. Now we'll be putting the value of W. W is balancing FV and W is balancing FV. So at a certain velocity, terminal velocity, the body is in equilibrium. The body is in equilibrium. So if it is in equilibrium, then we'll substitute V sigma G plus 6 pi eta RV is equal to V rho G. Correct? Weight is equal to FV plus FB. So let's do one thing. Let's put this V term here only. 6 pi eta RV is equal to V rho G minus V sigma G. So 6 pi eta RV is equal to, if we take Vg common, we are left with rho minus sigma. Rho is density of body, sigma is density of liquid. So from here, velocity is V G rho minus sigma by, this is 6 pi eta R. Okay, one thing class. Volume, this is the volume. Volume into density. Velocity is equal to volume. So volume of a sphere, volume is 4 by 3 pi R cube. For a sphere, this is how we write the volume, right? This is how the volume is written. Now let's substitute the value of volume. So velocity will be 4 by 3 pi R cube. This G, then rho minus sigma by 6 pi eta R, correct? So see what all things are getting cancelled. Pi will be cancelled. 2, here 3, 2 into 3. 2 into 2 is 4, 2 into 3 is 6. R cube will be R square. This R will be cut. So finally, what is the formula of terminal velocity? 2, this is R square. This is G, rho minus sigma. 3 into 3 is 9 eta. This is the derivation of terminal velocity and the formula. Tell me, it's clear? Write it down. Write it down from here. If completed, you can leave. We'll continue this in the next class, okay, on Thursday.
So kind of a teacher.